Battery technology is a field where progress is usually slow, incremental, and painfully constrained by material limits. The best lithium-ion batteries today deliver roughly 1,000 to 3,000 full charge cycles before degrading to 80% capacity. That already translates to 15 to 20 years of real-world electric vehicle use. Claiming a battery that lasts 30 to 50 times longer is not just bold, it is almost heretical. So the real question is not whether the claim is exciting. It is whether it is meaningful, reproducible, and relevant outside a laboratory. If you already have the answer, sign up to join our discussion about electrical technology in the upcoming episodes. To appreciate why 100,000 cycles sounds almost absurd, consider the math. One full charge per day is already aggressive usage for an electric vehicle. At that rate, a 100,000 cycle battery would theoretically last 274 years. Even accounting for partial cycles and real-world inefficiencies, the implication is clear. The battery would outlive the vehicle, the manufacturer, and possibly the infrastructure around it. In engineering, numbers like this immediately trigger suspicion, not because engineers are cynical, but because they understand context. Cycle life is not a single, absolute property. It is a result of test conditions, current density, temperature, depth of discharge, and mechanical stress. Change those variables, and the number can collapse dramatically. Donut Labs' explanation for achieving this longevity centers on material structure. Instead of using crystalline solid electrolytes, which are rigid and prone to cracking, the company claims to use an amorphous, non-crystalline structure. In simple terms, crystalline materials fracture under stress because they have ordered lattices that fail along predictable planes. Amorphous materials behave more like a sponge. They deform, compress, and recover without forming permanent cracks. From a materials science standpoint, this is plausible. Amorphous electrolytes can, in theory, tolerate ion movement without accumulating mechanical damage. If microcracks never form, interfacial resistance remains low, and degradation slows dramatically. This alone could explain why cycle life in controlled conditions appears extraordinary. But engineers rarely stop at "in theory." The uncomfortable truth is that cycle life records are often achieved under extremely gentle testing conditions, low current, narrow temperature windows, and minimal mechanical stress. Fast charging, especially 5-minute charging, introduces intense thermal gradients and localized stress. Real vehicles add vibration, shock, and long-term environmental exposure. Whether Donut Labs' amorphous structure can survive all of that simultaneously is still an open question. What are the bottlenecks in the manufacturing process of solid-state batteries? Even if longevity is real, manufacturing remains the historical graveyard of solid-state promises. Traditional solid-state cells require extreme stack pressures, often several megapascals, to maintain contact between rigid layers. They also require ultra-dry environments, with humidity levels below 1%, because moisture degrades ionic conductivity and interface stability. Retrofitting existing lithium-ion factories to meet these requirements is estimated to require replacing 80 to 95% of production equipment. This is precisely where Donut Lab claims to diverge from the industry. Instead of assembling rigid layers, the company describes its battery material as clay-like, produced using a nanofluid printing process. In this approach, the active material is deposited in a semi-fluid state and then solidifies into a cohesive structure. Theoretically, this eliminates the need for massive mechanical compression and allows batteries to be formed into non-traditional shapes. If accurate, this approach solves two problems at once. First, it reduces mechanical stress at interfaces, which directly supports longer cycle life. Second, it simplifies manufacturing, potentially enabling roll-to-roll or additive processes rather than heavy pressing systems. This is a significant departure from the paths taken by established players like Toyota and Samsung, whose solid-state programs remain constrained by yield and scalability, despite years of investment. However, cost remains the missing variable. Donut Lab states that its process is cheaper than lithium-ion at scale, but the only commercial product currently using the technology is the Verge TS Pro electric motorcycle, priced around $30,000 US. That price point suggests either low production volumes, high material costs, or both. Until the technology appears in mid-range consumer products, claims of cost superiority remain theoretical. Why is the scientific community cautious with solid-state battery? The skepticism voiced by researchers at institutions such as Princeton University and University of Illinois does not focus on any single metric. It focuses on the combination. An energy density of approximately 400 watt-hours per kilogram already exceeds most commercial lithium-ion cells by 60 to 80%. Fast charging in 5 minutes implies extremely high ionic conductivity and thermal stability. Operation from -30 degrees Celsius to 100 degrees Celsius spans a temperature range that challenges even mature chemistries. Adding 100,000 cycles on top of that pushes against known trade-offs. In battery engineering, improvements almost always come with penalties. Increasing energy density typically accelerates degradation. Expanding temperature range often reduces lifetime. Fast charging increases mechanical and thermal stress. Technologies that claim to eliminate all trade-offs simultaneously face an extraordinary burden of proof. Another factor driving doubt is the absence of peer-reviewed data. Donut Lab has not published detailed electrochemical curves, impedance growth data, or long-term cycling results under automotive duty cycles. From a scientific perspective, this limits independent validation. From a business perspective, it reflects a desire to protect intellectual property in a highly competitive field. Instead of academic transparency, the company has chosen operational validation. Delivering vehicles equipped with its batteries as early as March 2026 is a high-risk, high-signal move. Real customers will expose weaknesses far faster than controlled experiments ever could. Despite the unanswered questions, dismissing Donut Lab outright would be intellectually lazy. The company is backed by Risto Silazmaya, a figure known for conservative governance and technical scrutiny rather than speculative hype. This does not guarantee success, but it significantly reduces the likelihood of deliberate misrepresentation. More importantly, even if the 100,000 cycle figure proves achievable only under limited conditions, the underlying idea that mechanical behavior may matter as much as electrochemistry could reshape how batteries are designed. If amorphous, deformable structures can meaningfully extend lifetime, future energy storage may evolve away from rigid crystalline assumptions that have dominated the field for decades. From a neutral engineering standpoint, the most accurate conclusion is this: the 100,000 cycle battery is neither confirmed immortality nor obvious fantasy. It is an extreme claim entering real-world testing, where statistics, physics, and customer usage will decide its fate. And regardless of the outcome, the discussion it has triggered is valuable. Because in energy storage, progress rarely begins with certainty. It begins with numbers bold enough to challenge what we think we know. What do you think about this? Leave a comment below and also discuss the current bottlenecks facing solid-state battery technology. Thank you all for your support. Thank you, fellas.